All right, guys, so I promised in class that I would do a couple more examples of the indeterminate powers limits. So let's do that. This will be a good time. So let's look at the limit. Here's another example of one. As x, we'll do kind of a simple one here, approaches 0 from the right of x to the x. So this example, what's my indeterminate form here? Well, clearly x goes to 0 as x goes to 0. So my indeterminate form then is going to be 0 to the 0. All right, so 0 to the 0, remember our first step here? We're going to take whatever we're taking the limit of, rewrite that as y, and then again, we're bringing in the natural log of x. Nope, we're not. We're bringing in just the natural log of both sides. And the whole reason we do that is to make sure, it's basically to use the natural log for its property that I can bring down the exponent. Okay, so I'm going to take the limit as x approaches. So what am I approaching? So I'm going to take the limit of the same thing, of the same thing that I have up here. So I have x going to 0 from the right. So that's what I'm going to take the limit of up here. And I'm just going to take the limit of both sides of this equation. So now I have the limit as x approaches 0 from the right of x natural log of x. And we did this one in class, right? We looked at what's happening here. So this guy right here is going to 0. This guy is going to, well, we did one, I think similar to this, minus infinity. So now I have an indeterminate form of basically 0 times infinity, right? That 0 could absorb the negative. And what was kind of our method for evaluating a limit, an indeterminate form such as this, is remember, I want everything to become a L'Hopital. That's my goal. So when I have something like this where it's a product, what I'm going to do is I'm going to rewrite one of these. I'm going to put one of them on the bottom. And in this case, I'm going to go ahead and do put x on the bottom, right? Because it's just going to be a little bit easier than if I put the natural log of x on the bottom. Again, my goal is to use L'Hopitals. So I'd rather take the derivative of 1 over x than the derivative of 1 over the natural log of x, which would be a whole chain rule fiasco and, you know, blah, blah, blah. So what are we going to have here then? As I go to 0 from the right, the top is going to minus infinity, right? And then 1 over 0 from the right, that guy's going to infinity. So this is really good news because I'm going to have basically infinity over infinity. Remember, you have to tell me the indeterminate form, and then you have to indicate that you're using L'Hopitals. So the derivative then, so now I'm ready to take the L'Hopitals of this. So the numerator, I take the derivative of the top, that's 1 over x. The derivative of the bottom, I can think of that as x to the negative 1. Its derivative is a negative x to the negative 2, which I can rewrite as a negative 1 over x squared. So this is negative 1 over x squared. Let's simplify this a little bit. What would this become? This is 1 over x times a negative x squared over 1, which in this case then is just a negative x. So look at what we have here then. I get the limit as x approaches 0 from the right of a negative x. So what's happening? X is obviously going to 0. A negative x, or a negative 0, is also known as 0, which we showed that before in class. Okay, we're not done now. So let's write down, I'm going to come back up here. Let's write down what we know then. We know then that the limit as x approaches 0 from the right, not of y equals 0, but what of the natural log of y equals 0. So you're not quite done yet. So when you do something like this where you have to bring in the natural log in order to get that exponent down, you have an extra step at the end. So what's my extra step at the end? So remember, because natural log is a continuous function over its domain, I'm allowed to bring in an e. So I'm going to e both sides, right? I'm going to take e raised to the natural log of y and e raised to the 0. I can do that. Why do I do that? Whoa. Why do I do that? Because then the e and the natural log cancel. So I'm left with the limit as x approaches 0 of y, right, equals e to the 0, and e to the 0 is 1. And we're done. Why are we done? Because what did we define? What was our original goal, right? To take the limit of x to the x as your x approaches 0. I let y equal x to the x, so that's exactly what I've shown that limit to be. Isn't that great? Oh, that's a good one. Let's look at one more example, and then we're going to move on to 4.9, which is kind of the purpose of this lecture, really. So one more example with this. Let's take the limit as x approaches, again, 0 from, whoa, settle down there, 0 from the right, of 1 plus the sine of 4x all to the cotangent of 4x. Ooh, this is going to be exciting. I'm actually not quite sure what's going to happen with this, but I know it's going to be great. Okay, so let's look at what my indeterminate form is. If I put in 0 for x, the sine of 0 is 0. So that's just, the inside's just going to become 1. Let me do that in a different color. So the inside's just going to become 1. And then the cotangent of 4x, so remember cotangent is cosine over sine, right? Cosine over sine. Sine of 0 is 0, so I guess 1 over 0, which is infinity, basically. So my indeterminate form, make sure you're able to state what your indeterminate form is. You should be doing that on your homework, stating each indeterminate form. So again, if I get one of these indeterminate powers, I rewrite it. I'm going to let I'm going to let y equal whatever I'm taking the limit of, right? And then we're going to take the natural log of y, or of both sides. And the whole reason we do that, people, is so that I can bring that exponent down. That's the goal. So I bring that exponent down. And now I'm just going to, honestly, I'm not exactly sure what's going to happen here, but I think what's going to happen is I'm going to end up getting like a 0 over 0 kind of situation. But I know that I want to use L'Hopital's, and I know that L'Hopital's requires a fraction. So I'm going to rewrite this. So cotangent is cosine over sine, right? So I'm just going to rewrite this really quick as cosine over sine. Ooh, maybe I don't want to do that. I'm lying. I don't want to do that. Here's why I don't want to do that. If I write that as cosine over sine, I'm going to have to do product rule on top, and I really don't want to do product rule. So what else can I write cotangent as? That's 1 over the tangent of 4x. That's the definition of cotangent. Let's do that instead. So I'm going to rewrite this as natural log of, I forgot my sign. You guys probably noticed that before I did. Oh my goodness. This is why I shouldn't be teaching to a computer, because you guys are my checks and balances. That wouldn't have been wrong, by the way, to, hold on, I'm going to see if I can. That would have been wrong to write that as cosine over sine, but I'm just trying to make this a little bit easier, because I know when I do L'Hopital's, I'm going to take the derivative of the top over the derivative of the bottom, and I just, in this case now, I avoid using the product rule, which nothing against the product rule, but all right, so now I'm going to take the limit. How do I know it goes to 0? Because that's what my original one was. I'm going to take the limit of both sides. You need to show all of these steps. You guys should be trying to mimic your work exactly like I show you. I am so bold as to say that. So let's see what happens here. Hopefully we're in a situation where we can use L'Hopital's, and I think so. So if we look at what's happening, let's get some pretty colors. That's fun. If I look at what's happening on the top, as x goes to 0, I get the natural log of 1, right, which equals 0 on the top. And then all over the tangent of 0, which the tangent of 0 is 0 now, because that's sine over cosine, so that's not undefined. So I'm going to use L'Hopital's. So I'm going to rewrite this. I remember you have to state the indeterminate form and then state you're using L'Hopital's. I will take off on the exam if you do not do so. Wow, that's mean. All right, so here's what we get over here, 1 over the stuff. So I get 1 plus sine of 4x times the derivative of the stuff. So the derivative of the stuff would be what? 4 cosine of 4x, right? And then tangent of 4x is secant squared of 4x times 4. And now, as usual, the hardest part about this is going to be simplifying. But what I can do is I can look at this and kind of see, let's mess with this a little bit. So equals, remember I'm bringing my limit sign because I haven't actually taken the limit yet. And let's see what we get here. So this guy right here, right? This is secant squared is cosine. So this really is 1 over the cosine squared of 4x. And that 4 right there would go in the numerator. So what do I do when I divide fractions? We flip it and multiply. So I think this is actually going to work out pretty nice. We may have to do L'Hopital's one more time, but we may not. So who knows? So I'm going to, I don't think we're going to have to actually. I'm going to flip this guy and multiply. So this becomes cosine squared of 4x all over 4. My 4's cancel. So I have the limit then as x approaches 0 from the right of cosine cubed of 4x all over 1 plus 4x, sine of 4x. Oh, I don't have to do it again. That's pretty cool. Although I like doing it, so, you know. All right, what happens here? Cosine of 0 is 1. What is the sine of 0? Sine of 0 is 0, but that's okay. So the top is going to 1 cubed technically, and the bottom is going to 1 plus 0. So what do I get for the limit? And I'm going to rewrite this. The limit then as x approaches 0 of the natural log of y, right, is going to equal 1, it looks like. You're not done? So what is the actual limit then? That then means that the limit of the actual function that I care about, which is 1 plus sine of 4x all to the cotangent of 4x, is not just 1, it's e to the 1, which is just e, which is pretty crazy to think about, that that I'm taking the limit of something with some sines and cotangents in it and I get e, but that actually works out because there's a different definition for e with limits. I think maybe we talked about that. All right, guys, those are the two examples kind of that I wanted to do from that section. If you are not in class today, which is Wednesday, I'm recording this, you need to get the notes from someone. There is a specific way I want you to write your answers, and if you don't do it that way, I'm taking off. So you should come to class. We have fun. All right. So let's actually get started on the section that I wanted to cover to make up for missed class on Friday. So this is 4.9, and this section is called antiderivatives. Oh, come on. All right, maybe. Antiderivatives. That sounds kind of mean, but it's not. I promise. It's actually pretty cool. So here's the idea. The idea that we're going to kind of talk about today is, this section talks about, is equally as important as taking derivatives, is what if I am given a function? So if I know, let's say that that I have some function 2x, can I find a function so that I know that this is the derivative of that function? So we're going the opposite way. So we used to take, right, we know that the derivative of x cubed is 3x squared. The idea here now is, what if I gave you 3x squared, right, and you didn't have any of this? Could you find the function whose derivative is 3x squared? So we're just basically going backwards. Okay, so let's write down this as a formal definition, and then we're just going to do kind of a bunch of examples, see if we can find some patterns, and maybe write down some rules. We had the power rule for taking derivatives. We're going to have a power rule for taking an antiderivative. So let's go ahead and write down this definition, and then we'll kind of start having some fun. So definition. So we say that a function, and we call this capital F, is an antiderivative of a given function. So let's say you're given some function little f on some interval I, right? Doesn't have to be, we always say that so that we can mathematicians just say that so they don't have to say it's true like all over the real numbers or something. This is called an antiderivative provided that the derivative of capital F is little f for all x in that interval. Okay? I wonder if I can make this, anyway, there should be a little x in there. Sorry about that. So that's what we mean by an antiderivative. So this function f is an antiderivative of this little function here if its derivative is that little function, right? So for example, if I give you that little f of x is 2x, can you find, now I want you to pay close attention to this right here. What is this, an article or something in English? I don't care. I don't remember what it is. But what's important about that is it says it's an antiderivative. It doesn't say it's the antiderivative. There are actually an infinite number of antiderivatives given a function. And why is that true? I'm pretending in my mind that you're answering me. It's because, you guys, the derivative of a constant is 0. So if I look at something like this, little f of x equals 2x, right? Could I find the antiderivative? Well, think about this. What function do I know whose derivative is 2x? Obviously, I hope that's obvious. It's x squared, right? The derivative of x squared is 2x. So this function right here, x squared, is an antiderivative of 2x because its derivative is 2x. But guess what else is an antiderivative of 2x? X squared plus 7, right? Take that derivative, the x squared plus 7, what happens to the derivative of 7? It goes to 0. X squared plus 79 is an antiderivative of 2x. X squared plus 79 times e is an antiderivative of 2x. So we have to be a little bit careful when we take these antiderivatives because there's going to be a constant in there. So we'll talk about that later. We'll talk about, well, not later, we're actually going to talk about that right now. So that's what we mean when we talk about these things. You know, another example we saw that before was like that 3x squared. We saw what is its antiderivative, what function when I take its derivative is 3x squared, x cubed. But of course I could add any number to it and that would also be an antiderivative. So here's what we do to get around that. What we do is we add, it's not a variable, but we add a letter to this and we call that, we say it's plus c. That's a capital C. And what that letter stands for is that it is a constant. So what this does for us, oh man, sorry. There we go. This guy right here then provides me with what we call a family of antiderivatives. We say that this function, capital F of x equals x squared plus c, basically represents all possible antiderivatives of 2x because any constant could be added into this function and its derivative would still be 2x. So let's write that down really quick as a theorem. So let's let f of x, capital F of x, be any antiderivative. So it could be the antiderivative with 0, it could be the antiderivative with whatever. Usually we pick the antiderivative with constant 0. Okay, so be any antiderivative of little f on an interval, blah, 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 right? Then all antiderivatives, so all antiderivatives then of f on the interval I have the form, we just add that c. F plus c, and then let's say what c is, where c is any arbitrary constant. Now, I'm going to tell you right now, arbitrary, I think that's you're going to forget to add the c. Don't forget to add the c. We must add the c because when we are asked to find the antiderivatives of a function, we want to represent all possible antiderivatives. And because the derivative of a constant is 0, that means that we have an infinite number of possibilities for those antiderivatives. Okay, so let's look at a couple examples of this. All right, so let's find the antiderivative of each function. And let's just kind of do this thinking about what we know about derivatives, right? Which, you guys, we've been doing derivatives now for like 14 weeks. Hasn't it been of each functions? Hasn't been the best 14 weeks. I totally agree. So what about if I give you f of x equals the cosine of x? So what is its antiderivative? So remember, I need to just find one antiderivative, so we'll just find the one with the constant 0. And you find a function whose derivative is cosine, sine. Right? Whose derivative is cosine? That would be sine plus of course any constant, right? If I took that derivative, that constant would go to 0. Here's the nice thing about taking antiderivatives. You can always check yourself. How can you always check yourself? By taking the derivative of that function. If you take the derivative and you don't get this, something is wrong, okay? So likewise, what if I had f of x equals sine of x? So you might say to yourself, I think that its antiderivative is cosine of x plus c. And then your self would answer back, I don't know what's happening here. Well, but self, if I took the derivative of cosine of x, right, because I know that c would go to 0, I know that the derivative of cosine of x is a negative sine x. So I don't want a negative sine x, right? I want a positive sine x. How could I get rid of that negative sine x? I'm going to actually just put a negative in front of cosine, because now if I check this, then the derivative of a negative cosine of x, right, would be a negative of the derivative of cosine of x, which is a negative sine x, and that would be positive. So that is how you're going to check yourself when you're dealing with these antiderivatives, okay? Some of this is, let's talk about some notation here. Well, actually, before we get there, let's put that back in. What about f of x equals like x to the 5th plus 1? So I want to find a function whose antiderivative is x to the 5th plus 1. And I'm getting a little bit ahead of myself because I'm saying we can go over addition, which we don't technically know we can do that, but we can. It's okay. So if I look at this, we need to take the antiderivative. Let's kind of see what we think it might be. So capital F of x, how would I get to x to the 5th? So let's remind ourselves what the power rule does. Like if I were to take the derivative, let's say, of x to the 7th, right? The derivative of x to the 7th, I would bring the 7 down and I would take 1 away. So to get to x to the 5th, I must have had something that was one degree higher than that, right? Because I would have had to subtract to get to the 5th. And then to get the 1, well, what function whose derivative is 1? That would just be x, right? The derivative of x is 1. And then I have that c. So this is my conjecture that the antiderivative of x to the 5th plus 1 is going to be x to the 6th plus x. But if I take that derivative, people, notice we get 6x to the 5th plus 1 if I take the derivative. That's close. But what do I want? I want a 1 in front of x to the 5th. I don't want a 6. So how would I get rid of that 6? I'm going to put a constant in front that would divide it out. Okay? So this is what we call the power rule for anti-differentiation. And basically, if you think about it this way, when I take the derivative, I multiply and then take 1 away. When I take the antiderivative, notice what I did. I added 1 and then I divided by it. So taking the derivative, the power rule was multiply and subtract. If we're doing the antiderivative, it's add and divide, okay? And so let's write that down kind of as a little rule. Also, I'm kind of sick of writing antiderivative, aren't you guys? I know I am too. So let's talk about some notation that actually is going to make it a little bit easier to indicate that, hey guys, I want to take the antiderivative, and that's what we call an indefinite integral. Okay, so an indefinite integral, this is kind of just a definition or some notation. And this notation is going to give us the ability to indicate that I know I already said this, that I want to take the antiderivative, okay? So, oh, come on. There we go. All right, so this is what we call the indefinite integral. So it's kind of this long S looking thing. We'll talk about why it's a long S looking thing later on in chapter 5. But what we do with this indefinite integral is we have this this little long kind of S, and then what we put the function that we want to find the antiderivative of, and then again we'll talk about kind of where this sign here comes from and where this comes from later. But the dx really just tells us what variable we are taking the antiderivative of with respect to. So this guy right here is called an indefinite integral. It tells us to take the antiderivative of the function inside. Oh, what am I doing? Indefinite integral. This whole thing is called an indefinite integral. Okay, this guy right here, then the function that I want to find the antiderivative of, this is called the integrand. And that's just the function that I want to find the integral of. And then, let me get another color just because it's fun. This right here is what we call the variable of integration. So this just tells me, yep, we are integrating with respect to x. When we get to Calc 3, I believe it is, Calc 3, maybe sooner than that, we can integrate with respect to different variables. But for right now, we're just going to integrate with respect to x. That's why we kind of need that dx there, because it tells me I can integrate with respect to different variables. Okay, so that's what that is. And what does the indefinite, I guess I should tell you what the indefinite integral gives you. The indefinite integral gives you all antiderivatives of f, right? So this here represents all antiderivatives of little f of x. Okay. Okay, so let's start stating some theorems about this. So a quick theorem, this is going to be the power rule for indefinite integrals. So now instead of having to say power rule for antiderivatives of functions, anytime I say indefinite integral, if I say indefinite, that's just reflecting that we are going to have a definite integral later on. So don't let the indefinite confuse you. It's not that it's not defined or anything like that. We just call it the indefinite integral to counterbalance the definite integral later. So the power rule is it's kind of what I was talking about a little bit ago. If I want to find all antiderivatives of x raised to some number, okay, then what do we do with that number? Well, instead, remember the power rule for derivatives was to multiply and then subtract, right? So now we're going to do the opposite stuff in the opposite direction. So instead of multiplying and then subtracting, what we're going to do is we're going to add. So I'm going to add 1 to that p and then divide by it. And then of course, I'm going to have the plus c. Now one thing, and this is very, very important, this is true as long as p is not equal to -1, right? Very, 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 very important. P cannot be -1. So if I have x to the -1, which is the same as 1 over x, you cannot use this rule. Why can't we use that rule? Because we know that's the derivative of natural log, you guys. So this doesn't make sense. Now notice, this works, right? If we take the derivative of x to the p plus 1 all over p plus 1 plus c, right? This is how we check everything with antiderivatives. The c goes to 0. Here I would bring the p plus 1 down, right? And then I would take 1 away. And then the denominator is just p plus 1 because that's just a constant. Notice the p plus 1's cancel, the 1's cancel, and sure enough, I just get x to the p. Yay, this is so exciting. So let's do a couple examples with this. So the integral of x cubed dx. I'm going to add 1 to 3. Adding 1 to 3 is 4, and then I'm going to divide by it. And then I'm going to put a plus c. Simple as that, you guys. There's my antiderivative. A lot of times I will write this as 1/4 x to the 4th. I don't know why, that's personal preference. I just like to write it as a fraction in front instead. You don't have to do that, you guys. Seriously, you don't have to. Oh, we don't know we can do that yet. Hold on. What about something like x to the pi? I know that's silly. dx. It would still be x to the pi plus 1 because pi is a constant, all over pi plus 1 plus c. Also, remember, you can check yourself. So like this one right here, if I were to take the derivative, that would be 1/4 times the derivative of x to the 4th is 4x cubed. The derivative of c is 0. So sure enough, I get x cubed. Check yourself before you wreck yourself. How many times do I have to say it? Huh? Check yourself. Although I didn't say that a bunch, I guess, because we weren't able to really check ourselves right with the other ones. A couple other theorems that we need, because we just introduced this indefinite integral, something that we haven't seen before, something that's new and shiny, but we need to be able to say a couple things about this. If I have the integral of a constant, now this is a little c, this isn't my arbitrary constant, but it is still any constant, I can actually bring that constant, and I was going to do that up here and then I didn't do it because I knew we hadn't stated this yet, but this makes sense, right? This is for a real number c. No, that's not how you spell I'm going to just put 4, because I'm lazy, C, an element of the real numbers, okay? I hope this makes sense. We know we could do that. You know, if I had 37x cubed and I asked you to take that derivative, you would take the 37 and then multiply by the derivative of x cubed, right? So that should also work going backwards because we're just taking the antiderivative. And we'll do some examples with that. And then also the sum rule, which kind of, because I have the C rule up here, this incorporates a difference rule also. But the nice thing is with indefinite integrals, and this is true for, right? If it's true for derivatives, it should be true for indefinite integrals because that's just the antiderivative of it. I can distribute integration across addition. I can actually distribute integration across subtraction also because if C was -1, right, I could just pull that -1 out front. Okay, so this is good news. So let's look at another example. How about then the integral of 3x to the 5th minus 4 plus 7 times the square root of x dx. Now I'm going to show each step. You wouldn't have to do this, right? But technically my theorem above says that I can separate, oh, I need my dx's. You need a dx with each of these. Notice how I have a dx with each of these. It kind of distributes through because I'm writing them as separate. I'm writing them as separate integrals now. I don't know why that became a minus. I'm going to rewrite this as x to the 1/2. You're going to get used to that. So just like when I took the derivative, I would want to write that as something to the 1/2. When I take the antiderivative, I want to use the power rule. So what else does the power rule say? I can, or this theorem say I could pull the 3 out. You guys are not going to do this on all of this. I could actually pull the 4 out and I would have 1 dx, right? And pull the 7 out. And I had to have x to the 1/2 dx. Oh my goodness. You're really not going to do that every time. But I want to show you that where that theorem, which I didn't prove for you, works. And you can actually prove those. It's pretty easy to prove those. All right, so now what do I do with my exponent, right? I add 1 and then divide by it. Okay, now what I want to show you here, well, let's just keep going really quick. Then I'm going to have minus, what's the antiderivative of 1? It's just x, right? That's the function whose derivative is 1. Then I have 7 times, okay, 1/2. Let's talk about fractions. Plus 1. You guys will not put x to the 1.5. I will take off. We don't ever write, we never write bases with exponents that are decimals. In my class, you will not do that. So I have 1, but what is 1? 1 is the same thing as 2 over 2. So 1/2 plus 2 over 2, that's x to the 3/2. So I add 1, and then you divide by it. You do that rule, okay? And then this whole thing, right, we add a c. One quick little thing about this. Technically what has happened is this has added a c, this one has added a c, and then this one has added a c. So what we like to do with these arbitrary constants is we say, well, what if I combined all these? They're all constants, right? So I could add them all up, and I could basically just make this all the constants added up together, and I'm gonna just call it c. Okay, so that's what there technically is a c from each one of those, but we're just gonna add them up and it's still gonna be a constant, so I can still just call it c. Now, of course, we're gonna simplify. 3 over 6 is also known as 1/2. X to the 6, can't really do anything with that 4x, but what happens when I have 1 over 3/2, that flips and multiplies, right, and becomes 2/3. So that's 14/3 x to the 3/2, all plus c. You'll get in the habit of that when it's a fraction exponent. You'll get in the habit of it because you know you're going to be dividing by that fraction. You'll just automatically flip it and multiply. So you'll get used to that, don't worry. What about something like this? How about the integral of x to the -2 minus 3x all over the square root of x dx. Oh. Think about if I asked you to take the derivative of this, and let's say we would have had to, okay, I'm just going to tell you right now, you cannot take the antiderivative of the top over the antiderivative of the bottom. We know you can't do that with derivatives, so it's not going to work with antiderivatives either. So we don't really have a quotient rule for the integral, so I have to mess with this somehow. Because if I'm asking you to do it, I'm clearly asking you to do maybe some sort of algebraic manipulation to it to get it into some form that I can actually use. So just like we would have with if I had asked you to take the derivative of this, what I'm going to rewrite this as is I'm actually going to rewrite this as x to the negative 1/2. There are a couple ways you could do this, or you could divide each term by x to the 1/2. That would be fine also. But I'm just going to rewrite it as x to the negative 1/2, right? That's this guy right here. I just rewrote as x to the negative 1/2. And now I'm going to take this through and combine like terms. So if I combine like terms, that's negative 4/2 minus 1/2. That would be a negative 5/2. Okay. Minus 3, this is x to the 1. 1 minus 1/2 is 1/2 dx. So do you see now, notice notation-wise, I kept my integral sign because I haven't actually taken the antiderivative yet. All I actually have done is rewritten it into something that is useful for me. Okay, now I'm ready to take the antiderivative. So let's do a little bit of side work. So for the first one, I'm going to take a negative 5/2 plus 1. That's the same thing as a negative 5/2 plus 2/2, right? That's the same thing as 1. So what does this become then? This becomes x to the negative 3/2 and then divide by it. Divided by negative 3/2 minus 3 x to the, what's 1/2 plus 1? We already saw that. That's 3/2 divided by 3/2, then all plus c. Now don't you dare leave it like that. What happens when you divide by a fraction? You flip it and multiply. So I get a negative 2/3 x to the negative 3/2, right? Minus 3 times 2/3. Oh, I didn't even mean for that to happen. X to the 3/2 plus c. So what's my final answer? What is the antiderivative in the most useful form? Well, I don't know if this is the most useful, but I get negative 2/3 x to the negative 3/2. My 3's cancel here, so I get minus 2x to the 3/2 plus c. We're done. Notice I want you to notice a couple of things here. If I brought this down and I multiplied it times the numerator or times the constant in front, I get 1, right? That is what I should get because there's a 1 in front of this term right here. Also, if you did take the derivative of this, you are not going to necessarily get this out right away. What you will get out is you'll get out this function right here. To get it all the way back to this guy right here, you would actually have to kind of go back to this step. So sometimes when you take that derivative, it doesn't hitch in the face as much as some of the other ones. Because if you have to do algebraic manipulations, it might not be as easy to see that that was the original integrand that you started with if you have to do some algebraic manipulations to it. Okay? Okay, guys. What else? Let's look at some different functions. So let's talk about, what I would like to do is just create a list of indefinite integrals that we should know. These are going to be kind of some other rules that we should know. I'm trying to see if they put this on your, no, they don't. So we're just going to write them all down together. So let's write down a table basically of indefinite integrals that you should know. You should write this down somewhere. Indefinite integrals, some important, they're not all of them, but let's write down some rules for some indefinite integrals. Or some antiderivatives, right? Because oh, come on. That's exactly the same thing. Indefinite. Sorry about that. Integral table, basically. All right. So, the first one. The integral of 1 is just x. And we have to have a plus c, right? That's 1 dx, so that's just going to be x. To the power rule, right? The integral of x to the p dx is going to be x to the p plus 1 all over p plus 1 plus c. That's called the power rule. Okay, let's look at now let's look at our trig functions, all right? The integral of cosine, we saw this before. The integral of cosine, whose derivative of cosine? That would be sine, right? So that's sine of x plus c. What's the integral of sine? Well, we saw this also. The integral of sine, because the derivative of cosine, right, is negative, the integral of sine must be a negative cosine of x. So remember when we took the derivative, the integral of, or the derivative of any of those trig functions starting with c was negative, it's going to be the opposite now. So any of the integrals of trig functions that don't start with c are going to be negative, because we got to get rid of that negative from when we take the derivative. What about, so integral of tangent I can't do. That's actually not true. We can do the integral of tangent eventually, but I don't know a function whose derivative is tangent. But let's think about what is the derivative of tangent, right? The derivative of tangent is secant squared. So I could actually take the integral of secant squared. I know that that must be tangent of x plus c, right? What about cotangent? So I can't take the integral of cotangent, but I know that the derivative of cotangent is cosecant squared. Oh, did I say the antiderivative of those without c's? That's not true. Please don't listen to me. Don't listen to me. But the derivative of cotangent is a negative cosecant, so the antiderivative would be a negative cotangent. I'm sorry about that. Don't listen. I mean, I do want you to listen to me. I mean, that's not true, but what else? So the derivative of sine is cosine, derivative of negative cosine is sine, the derivative of tangent is secant squared, the derivative of a negative cotangent is cosecant squared. What about the derivative of secant, right? What's the derivative of secant? That's secant x tangent x. So that means that the antiderivative of secant x tangent x is secant of x plus c. Okay. Let's keep going. What about cosecant? The derivative of cosecant is a negative cosecant cotangent, but I don't have to worry about that negative. So the antiderivative of cosecant cotangent is a negative cosecant. Gotta know these guys. Just like you had to know the derivatives of the trig functions, you need to be able to recognize the antiderivatives of all of these guys right here. Okay, and those I just got from taking the derivative, right? So you need to know all of those. You're welcome. Okay, some other ones that we need to know. So let's talk about what other derivatives we know. Well, we know the derivative of like e and natural log, right? So the derivative of e is e. So this one is lovely. This one's our favorite one. What's the antiderivative of e then? It's just e. That's so great. Now let's look at, we don't know a function whose derivative is natural log. We'll talk about the antiderivative of natural log later. But I do know that the derivative of natural log, right, is 1 over x. So when I take the integral of 1 over x, the antiderivative, now there's a couple things here you have to be careful of, and I want you to pay close attention to this. In this case right here, when my integrand is 1 over x, the only requirement on x is that it isn't 0. That's the only thing. There's no requirement on x being positive. There's no requirement anything about the actual sign of x. So when you take the antiderivative of 1 over x, it's not just the natural log of x, it's the natural log of the absolute value of x. And we did prove, if you go back and look, that the natural log of the absolute value of x is 1 over x, okay? You must have those absolute values because this x right here had no restrictions on it. Natural log you can only take the natural log of a positive number. And so that one right there, I need you to really remember that there's an absolute value I will take off for that because it won't be correct. Natural log might not know what to do with that x if that x isn't positive. So if that x is negative, we have to take the absolute value of it. Okay, let's see, a couple more that we're gonna see. 11, this one you might not remember. This one I would definitely give you 1 over the square root of 1 minus x squared dx. I don't know if you remember this, but that's the derivative of sine inverse. Okay. For cosine inverse, there's a negative in front, but then what we would just do if there's a negative in front is we just make that negative sine inverse. So when we look at the inverse trig functions, the antiderivatives, we usually just pick kind of one or the other. So like cotangent and tangent are almost the same. We know this one. What is the derivative of inverse tangent? It's 1 over 1 plus x squared, right? Remember the derivative of cotangent is just the opposite sign, S-I-G-N. It's a negative of it. But with the integral, the antiderivative doesn't know. So that negative I could just put in front and I could say it's a negative tangent inverse of x. So that's why we only worry about one set of them. So that's going to be the same thing then when we're dealing with secant. Now secant we have to be a little bit careful of. Remember we had an absolute value of x right there. So when again, the integrand does not put any restrictions on x. So we have to make sure that I take the secant inverse, the absolute value of x plus c. Okay, so this one also, secant inverse, you have to put that absolute value of x around it. No, I don't want to go to the internet. Okay, you guys. I hope that kind of makes sense. Let's do a couple examples here. I want to find the example I want, and then we want to talk about initial value problems, and then that's it. Oh my goodness, this was a lot. So, couple quick examples. Okay, so let's look at something like this maybe. How about secant theta tangent theta minus sine theta. Now I need d theta because I had thetas. All right, so what function when you take the derivative of it gives you secant tangent? That's just secant theta, right? So this part spits out secant theta. What's the antiderivative of sine? It's a negative cosine of theta. The other thing you could have seen there is you already have the negative, so I'm just going to get cosine plus c. So what's my final answer on this one? That becomes a positive. So my final answer is secant theta plus cosine theta plus c. And again, if you take that derivative, we get secant tangent, and then the derivative of cosine is a negative sine, and then the derivative of c, of course, is 0. What about something a little bit more exciting, like sine of x minus 1 all over cosine squared of x dx. Well, guys, on this one, here's what you can't do. Please don't. You may not take the antiderivative of the top over the antiderivative of the bottom, because the minute you do that, you're saying that when you take a derivative, you can take the derivative of the top over the derivative of the bottom. We're not doing L'Hopital's here, people. What we're doing is we're just trying to find a function whose derivative is sine of x minus 1 over cosine squared x. Okay, so what do? Well, we do some algebra. that's hopefully, right, what I can do. I'm going to do some algebraic manipulation to get it into something that I can work with. So there's not a whole lot I can do here, but one thing I could do is I have division. So I could rewrite this as sine of x over cosine squared x minus 1 over cosine squared x. So, when my trig students complain about simplifying trig expressions, this right here is how it's going to help us. Whoa. I don't know what just happened. Whoa. I'm using a new system. Look at that table of integrals. That is so great. Love it. Love it, love it, love it. All right. So I have, I broke it up. I want to try and find something that I can use here. So let's see if I can rewrite these in terms of like tangent or cotangent or cosecant, something like this. Sine of x over cosine squared. I could rewrite that as sine of x over cosine x times 1 over cosine x. And then this is still minus 1 over cosine squared x dx, right? And so why was this useful for me? Well, because what is this right here? This is tangent x, right? What is this? This is secant of x. What is this guy? This is secant squared of x, right? So now we're going to get a situation where I have secant times tangent, secant x, tangent x, order doesn't matter in multiplication, minus secant squared of x dx. And now I can take that antiderivative. What function's derivative is secant x tangent x? That would just be secant x, right? And then what function's derivative is secant squared? That's tangent. Oh, and then that's all plus c. Whew. I'm a little tired. I've been talking for 49 minutes straight. I know that surprises you, that I would be tired from doing that, but I kind of am. Let's just do one more, and then I think I'm going to call it good. We have one more small topic to get to in this section, but I think we can cover that on Monday. So one more example, and then let's call it a day, because we're at 50 minutes already. And if you're still with me in one sitting, I'm pretty amazed, honestly. Good on ya. I just want to make sure that the problem we do is something that is interesting and that is worth our time and that we can actually do. That's always helpful. I'm not gonna put a bunch of stuff in together here just because I want to. What if we had the square root of x minus 1 all over x plus 4e to the x? Yeah, that's good. Dx. Okay, so right now I can't do much with that fraction. So what I'm going to need to do is I'm going to need to simplify this a little bit. So what is this going to equal? This is x to the 1/2 over x. Now I'm dividing by each one. I don't know. Sometimes I bring it up as x to the -1. Sometimes I don't. I actually do know. Let me tell you why I didn't bring that up as x to the -1. Because I know that x to the -1 you may not use the power rule on. And I can see right here when I divide that 1, I'm going to get a 1 over x. And a 1 over x is natural log. It's not the power rule. Okay, so let's simplify this a little bit. Now you can't just like take the antiderivative of this term and not do it over here. So I'm going to rewrite this really quick. If I subtract those, that's going to be x to the -1/2 minus 1 over x plus 4e to the x dx. All right, so now we're raring to go. So I get x to the, whoa, I don't know why I switched that to blue. I didn't mean to. So I get x to the -1/2 plus 1 divided by a -1/2 plus 1 minus, guys, this is not the power rule. If you try and do the power rule and make that x to the -1, look at what's going to happen. You get -1 plus 1. What is that? That's 0, but then you're supposed to divide by it, and then all the bad things happen, right? So what is the antiderivative of 1 over x? That's the natural log of the absolute value of x. Can't forget that absolute value. And then here I'm going to just rewrite the 4. What's the antiderivative of e to the x? E to the x we love. E to the x is just chill. E to the x hangs out with everybody at the party, right? And so let's finally simplify this. -1/2 plus 1, that's 1/2, right? And 1 over 1/2 is 2. So I get 2x to the 1/2 minus the natural log of the absolute value of x plus 4e to the x plus c, and we are done. And you could take that derivative, right, and simplify it, and you should get this. Oh man, you guys, I'm kind of tired, but that was really fun. I enjoyed that. We still have a little bit more to talk about in terms of initial value problems. So initial value problems basically are given initial conditions so that you can find that C. That's not very hard to do. We can do that pretty quickly Monday morning and then continue on with the rest of, all of chapter 5 that we have to get through in a week and a half. I think we can do it. I think it'll be fine. Anyway, let me know if you have any questions. Even though I'm gone, I'll be checking my email. And enjoy. Have fun.